All right, let's just jump right into this explainer. Today, we're decoding a real-world detective story, and it starts with a massive, unprecedented digital blackout across an entire continent. I mean, imagine looking down at your navigation system, something your entire daily routine depends on, and suddenly, nothing. The signal is just gone, completely drowned out by some invisible force. So, we have to start by asking, what on earth could possibly overwhelm GPS signals simultaneously across such a massive area? Because, we aren't talking about a single neighborhood going dark or even a single country. This disruption literally stretched from Svalbard, way up in the high north, all the way down to Spain, and from Canada over in the west, stretching all the way to eastern Poland. And the reaction from the experts was pretty telling. University of Texas GPS expert Professor Todd Humphreys really captured the sheer scale and mystery of this whole thing. When he looked at the scope of this blackout, his reaction was that it was totally unprecedented. Humanity was dealing with something entirely new. Let's trace back how this investigation actually kicked off. In November of 2024, Professor Humphreys gets this mysterious tip-off, telling him to check out a specific set of publicly available data from monitoring stations. Well, when he and his students started digging back through that data, a crazy pattern emerged. These weren't just weird one-off glitches. They'd actually triggered 75 times since 2019, and almost always during business hours in Europe. And the sheer force behind this interference? It was staggering. Receivers all across the network recorded that the signal-to-noise ratio abruptly dropped by a factor of 10. Boom, just like that. The navigation signals were simply and totally overwhelmed. Section 1, the victim's vulnerability, or how navigation actually works. To really understand how this global system got attacked, we first kind of need to realize how fragile GNSS actually is, and how it figures out where you are on a map. Basically, your phone uses the time it takes for a signal to arrive from space to calculate your distance from a satellite. So, if you lock onto one satellite, you know you're somewhere on a giant sphere. Add a second satellite, and that intersection becomes a circle. A third narrows it down to just 2 exact points. But here's the catch. Your phone doesn't have a perfectly precise atomic clock, so its timing drifts. That means you actually need a 4th satellite to solve this complex 4-part equation to get your exact 3D position and correct that clock error. It's like a giant puzzle constantly being solved in your pocket. But here is an absolutely mind-blowing fact. Because the satellites themselves are constantly zooming around in orbit, they have to rely on ground stations right here on Earth to know their exact positions. And since the Earth's continents are constantly shifting around, those ground stations map the Earth by navigating using quasars. Yeah, quasars. Extremely bright radio sources billions of light years away. So we are quite literally navigating by distant stars. It's just being routed through your smartphone. So the crucial takeaway here is this incredibly tiny number. Think about it. By the time a GPS signal travels 20,000 kilometers from space, originating from a transmitter that's only pushing about 50 watts, it hits your phone at an insanely quiet 1/10 of a quadrillionth of a watt. A 1/10 of a quadrillionth! It is unimaginably fragile. Section 2, eliminating suspects, ruling out the ground and the sun. Now, because that signal is so fragile, jamming it is literally like yelling over someone who is whispering. So our detectives needed to start eliminating suspects. Right? Could a local radio tower do this? No way! The curvature of the Earth meant a ground tower, even in a highly militarized hotspot like Kaliningrad, couldn't possibly shout loud enough or even have the line of sight to affect all of Europe at once. Okay, well, could it be the sun? We know solar flares cause space-based interference, but solar events span a broad spectrum. They build up slowly over minutes, and they hit the entire sunlit side of the planet. This mystery interference was totally different. It was this narrow 5 megahertz slice. It triggered abruptly in just 3 to 5 seconds, and it was consistently centered right over Europe. So if it's not the ground and it's not the sun, it absolutely had to be a satellite. But there are over 15,000 active satellites in orbit right now. How do you narrow that down? Well, they applied a really elegant, simple geometric constraint. Whatever satellite did this had to be visible to all of the affected stations simultaneously during every single one of those 75 historical events. Using that rule, they slashed the suspect list from over 15,000 down to just 14. To get that massive line of sight across the globe, the culprit had to be sitting at least 1,200 kilometers high. Section 3, the missing clue, and how the trail goes cold. Unfortunately, for months, the trail went totally cold. Their prime suspect, an Algerian satellite, turned out to just be another victim whose legitimate signal was getting hammered by the interference. To break this case wide open, they needed raw radio voltage data, not just basic signal strength logs. And they finally got their hands on that in February 2026. This raw data let them use a really complex math concept called time difference of arrival, or TDOA. Basically, it's a method to find exactly where a signal's coming from by measuring the microscopic difference in when that signal hits two totally separate receiving stations. This ends up mapping out a massive 3D hyperbolic curve in space. And this incredibly high-resolution raw data revealed something amazing. The jamming signal reached a station in Trondheim, Norway, exactly 139 microseconds before it reached a station in Amsterdam. To put that into perspective, this highly specific timing constrained the source's location to a tight, warped surface in space with a microscopic margin of error of just 5 meters. Section 4. Unmasking the satellite. The culprit revealed. So, armed with this ultra-precise 3D map spanning just a 2.5-second window of raw data, the researchers tested the exact orbit of every known satellite against that curve. And the math pointed undeniably, flawlessly to one single culprit. When they overlaid the orbit onto their 3D map, Professor Humphreys noted that it wasn't just near the projected line. It was, in his words, dead on. The satellite was Cosmos 2056. It was launched in May 2020 as part of a 6-satellite constellation making up a Russian early missile warning system. Now it sits in what's called a highly elliptical Molniya orbit. Basically, that means it slows down and lingers way up high over the northern hemisphere. That specific altitude and coverage gives it the terrifying capability to jam GNSS across massive regions of the globe, even extending right over the United States. But there's a big lingering question here. Why broadcast a signal that is slightly offset from the main GPS frequency instead of blasting it directly on top of it? Well, two main theories pop up from the sources. The prevailing theory among researchers is that it's a periodic test of a capability that would be devastating if deployed in a hot conflict. They're testing it just off frequency so it doesn't cause total, catastrophic chaos. Yet. On the flip side, another independent team suggested these extremely brief bursts might actually be highly specific, covert communication messages. Which brings us to Section 5, protecting our fragile future, the invisible utility. Regardless of what the exact intent is, this whole revelation forces us to look at a much bigger issue. GPS is this invisible utility that underpins almost every single aspect of our modern world. It goes way beyond just getting driving directions. It synchronizes the timing of global financial systems, it keeps cell towers running, and it safely guides massive aviation and shipping networks. To survive this new era of space-based threats, we absolutely cannot remain entirely dependent on a signal that hits our devices at a tenth of a quadrillionth of a watt. We have to urgently build resilient backup networks. We're talking about terrestrial broadcasts like eLORAN using high-powered radio towers, running fiber optic cables to securely share atomic clock time across the Earth, or even using cutting-edge magnetic and quantum systems that read natural variations in the Earth's magnetic field. So, as we wrap up this explainer, I want to leave you with an even more chilling thought about our fragile technological future. Today, we've mostly been talking about jamming, right? Which is essentially just yelling over a signal to drown out the truth. But what happens when malicious actors start feeding our devices a geographic lie? What happens when ships and planes are quietly guided to impossible, dangerous locations without ever knowing their signals were hijacked in the first place? That's called GPS spoofing. And it leaves us with an entirely new, terrifying set of questions. Thanks so much for diving